Hi, my name is Michael Dickens. I'm a research scientist with HPRC, and I'll be covering submitting Slurm jobs. We'll go over submitting a Slurm job and looking at the resource usage and talk about the different types of jobs and how to configure single node, multi-node jobs and the types of resources you can select. Here's a summary of what we'll go over. We'll cover what is an HPC and look at some of the common SBATCH parameters that you provide for Slurm. Then we'll go over the single node jobs, both in a single core or multi-core. Depending on the software, if it supports single core or multi-core, you can configure your job specific ways. We'll have a short break and then we'll cover multi-node jobs. And there's a few different ways to run multi-node jobs. And then we'll look at monitoring resources at runtime and after we submit a job. And then we'll talk about a little bit about the Drona workflow engine. So this is ACES. You can see we've got a number of accelerators. Most everyone's interested in the H100s. Those are the high-end GPUs that we have. And we'll show you how to see how many of those are available and how many of those are configured and how many are available at the time you submit your job. We have a user guide in our knowledge base, and there's the link at the bottom. So we'll be working on the portal. This is the Open On Demand portal, and from our main website, or hprc.tamu.edu, you can access this mouse over portal, and then you'll see the ACES portal, and this is for access users. And then if this is your first time to log in for the day, you'll have to do the two-factor authentication. And but depending on how you registered for access, you may need to select access CI, which is formerly Exceed, or you can use your resource, your institution. You can find your institution here if you register with your institution. All right, so I'm gonna switch over here and mouse over portal. And there's the ACES portal. I've already logged in, so I'll skip the authentication screens. Now you can see we have a menu here, lots of selections here. What we'll be doing first is going to access the shell. So mouse over clusters. Actually, you got to click clusters and then click shell access. All right, so let's log into the portal and connect to the shell. And you'll reach what we call the command line. This is where you'll enter Unix commands. And then let's see what message we'll see and which login node we landed on. So what we see here, there was a message about adding this host to a permanent host. That's fine. And then we've got a default message here about using resources. And then we have links to our websites. Knowledge base, our main website, knowledge base. We also have a YouTube channel. We have contact information here. And then we have some information here you should read each time you log in red here. This red part will not change. There are only nightly backups of users' home directories. Scratch is not backed up, so these two will not change. And this other part here, a restricting 8 cores across all login nodes. This is for the login nodes. This is not for the compute nodes. When you submit a job, you can use all the cores on the compute node, and we'll show you how to query how many cores are on the compute nodes. And then you'll see if you want to run this, see this again, you can type in MOTD, the MOTD command, and you can hit enter and it'll show it again. Then you'll see your quotas. We have home quota and a scratch quota, and you have a group quota. Your home quotas, this is the one that cannot be increased. So this is a place mainly where a lot of software stores configurations. And it's a place where you can save your job scripts if you want those to be backed up. But as far as any data greater than 10 gigabytes, you'll have to move that data to your scratch directory, and that's not backed up. So you can see I've got 10,000 file limit, 5,000. I've already used 5,000 files. There are some hidden directories in your home directory. Sometimes those fill up with cache files and configuration files, installation files. The trick is to move that directory to a scratch directory and then create a symlink in your home directory that points to the scratch directory. That way, all those files in the cache directory don't get counted against your home quota. They'll get counted against your scratch quota, which has a lot more file space available. All right, so which login node do we land on? In this login session, I landed on ACES login 1. Others might see ACES login 2. It's just a way to distribute the workload across multiple login nodes, so we don't have 100 users logged into one login node. We can distribute that on 2 login nodes, and that way we have 50 on one node and 50 on the other. All right, Slurm, it's a workload manager used for on our HPC clusters. So basically what it does is it matches available resources with your jobs. When those resources become available, your job will be launched. You can schedule your job. When you submit your job, it will be scheduled and it will stay in queue until resources become available. Sometimes it's right away. Sometimes it can take a few hours, maybe even a day if you're trying to use the GPU resources. We have documentation about batch scripts. Here's a link here. And then we have the official Slurm documentation link is at the bottom of this slide. So we use these terms node and core, and so this is just a little bit details about what is a node. So a node is an individual computer unit. We have a lot of these computer units connected, wired together, cabled together, and they're interconnected into what we call the cluster. So each of these nodes, well, there's 2 types of nodes. The login node, this is where you log in. Like I was on login node 1. This is where you can do file editing. You can do some short testing of software. You can do software installation, and there are some limitations as to how long a process can run, 60 minutes. And so if you do have if you're running some test scripts and it finishes right at 60 minutes, just be aware that we have some scripts that will monitor processes and stop them when they reach 60-minute mark. In that case, you'll need to log into or start an interactive job on the compute nodes. Compute nodes, this is where most the heavy processing is performed. There are hundreds of compute nodes on our clusters. Some have hundreds, some have fewer GPU nodes or even fewer. And you'll specify in your job script what type of node and how many resources, CPUs, and how much memory you want to request for your job. If it's a GPU job, you request a GPU. If your software does not support GPU, then you'll not want to select the GPU node, reserve the GPU nodes for software that supports GPUs. Using the GPUs does cost more service units. I'll go over service units in a little bit. So basically, you don't want to just use a GPU node if you're not using the GPU resource, because they can be expensive if you run them for a couple of days. All right, cores. There's some interchangeable terms here. CPUs. Slurm uses the term CPUs. When you might be familiar with cores, your laptop has quad core or dual core. And you'll see that the ACES compute nodes have 96 cores or 96 CPUs. And also we've got, they have 488 gigabytes of available memory. And you'll want to also make sure the software supports multi-core processing before you select all 96 cores. If you select all 96 cores and your software only supports running on one core, then you'll have one core running at 100% usage, and you'll have the other 95 cores idle, unavailable for other jobs to be scheduled on those cores. So be aware of the software you're using and the type of resources it supports. Here's a typical HPC diagram. On the left, you'll see our login nodes. We have 3 login nodes. This is where everyone first lands when they log into the cluster, whether you're logging in. Actually, the only way you can log into the compute nodes is through the portal. So from there, you'll use some type of file editor. You can use VI. We also have an editor that you can use in your web browser. You can create files, manage files, delete files, edit files. I'll show you how to do that. And then once your file is ready, your job script is ready, you have your input files uploaded, then you can submit your job to Slurm. There are some Slurm commands for that. And then it will be placed in a job queue, and it will be assigned a specific partition. Some are automatically assigned, some you'll have to specify if you want to use certain accelerators. And then once the resources are available, your job will be moved to one of the compute nodes. Both the login nodes and the compute nodes have access to your home directory and your scratch directory. The compute nodes do have some maximum run times, and we'll go over how to view those maximum run times. But just remember the login nodes have a max runtime of task for 60 minutes, and you don't want to use more than 8 cores. But on the compute nodes, you can definitely run a job for a number of days, and we'll cover that later. All right, here's an example. Job script is just a text file. Basically, it is a text file of Unix commands. In Unix, any command that starts with a pound, or the pound or the hashtag sign symbol, that is lets in this case the very first line bash. So this is a bash script. So this lets bash know that this is a comment, and to ignore the sign to not actually do anything. So basically, you could enter pound SBATCH on the command line, it would not do anything. If you look further down, if you do module purge, that's an actual command. If you enter that on the command line, then it will purge your modules that you have loaded. So you can see this is the format. Again, it's a text file. You can name it whatever you want. It would be good to be consistent in your naming, because later you may want to search for all your job scripts, and that way you can have a pattern match. Maybe all your job scripts end with .job or .sbatch. Probably don't want to use common suffixes like .out or .in or .error or any other dot you can think of. So these are some suffixes that people have been using, users have been using. .job, .slurm. It is a shell script. You can use .sh. In this case, I usually start my job script with the word run, and then it ends with .sh. That way I can search for anything that starts with run and ends with .sh. So the top lines are the SBATCH parameters. SBATCH, pound SBATCH, Unix recognize this as a comment, but Slurm recognizes this as a parameter to apply to the job. In this case, job name, it will be called spades. And just avoid using spaces here. You can, after the job name, you can use spaces, and then you can add additional comments here. The first line, you have to leave it exactly as it is with no spaces after the word bash here. But here you can add comments and just to give a little bit of detail about what this line means. Some of them are pretty self-explanatory. The job name, time, this at least tells you the format. The first value here, 1, is the number of days. then there's a dash and it's hours, minutes, seconds. Sometimes it's easier just to request 1 day, 2 days. You can request 2 days. If you think your job will complete in 12 hours, it might be good to request 2 days. And we'll talk about that in a little bit. You'll be reimbursed for the unused time. Number of nodes. By default, if you schedule fewer than the number of cores on a node, it'll generally select 1 node, but that's not always the case. You may want to keep this in here. If the software supports multiple nodes, then you can test on a single node, and then when you're ready to move to multiple nodes, all you need to do is change this line to 10 nodes, for example. In task per node, CPUs per task. We'll go over that in a little bit. The term tasks, explain a little bit more what that is. Memory, this is the total amount of memory per node. You can select the maximum amount of memory, or if you're not sure how much memory it will use, your job will use. And then once you get an idea, I've been running this job a few times and it's never used more than 5 gigabytes of memory, so I can just schedule it with 20 gigs instead of using the full 488 gigabytes of memory. But if you are running if you need to, some software can utilize all the cores or all the CPUs, all 96. So if you're going to use all 96, you may want to go ahead and select all of the memory because you're basically will be charged for the service units for the entire compute node. And you don't want it to run for a day and a half and then you run out of memory at a certain step. So you want to keep, if you're going to request the entire node, just request all the CPUs and all the memory. There's a couple of different output files. Standard out, this is basically just what you'll see is some maybe some log information. Standard error, if there are any errors during the running of your job, whether it's from the software or from Slurm or anything, you can save that into a separate file. If you leave off this error line, both standard error and standard out, both these outputs will be saved to a single file called .output. But it may be good to separate these to make it a little bit easier to see what is the output and what is the error. %X takes the value that's in job name. So at the end, when this job is complete, you'll have standard out dot spades dot and then the %J, that's the assigned job ID. We don't know what that is yet until the job is launched, but it'll get appended to the name of the output file. Comments here again in blue, the pound sign. This just gives you information about what you're doing. It's pretty, in this case, it's some of these are kind of simple load software modules, but you may have a really long job script that has, you may not understand what a line means unless you go back to the top of your job script and read all the way down. So it may help to have a comment right before that line to remind you why you're running this line. And then you run your commands in this type of, this way. All right. So we talked about nodes. Basically, you can change this 1 to 10. It's good to test on 1 before you move to a higher number. In tasks, a task would be like a command that you run. If you're familiar with the some of the bioinformatics tools, blast in or BWA command, that would actually be a task, or your Python script would be a task. So in the bottom right image here, the task would be one task, which would be spades.py. It's a Python script. And the number of CPUs, you can specify this as threads. So you would schedule your job to use 1 task and then 1 CPU or 96 CPUs per task. So this task will be using 96 CPUs. And again, make sure that the software supports that many supports threads. If you were to run, actually, you can run the help for the software and it will let you know if it supports threads. That's another word that we use for CPUs. Or cores. Some software uses the term cores, some software uses threads. And you can look for that in the documentation for the software to make sure it supports multi-core, multi multi-core processing. So if you're scheduling in task, make sure you either use nodes or task per node. Otherwise, if you schedule 96 tasks and you don't specify nodes or task per node, you will most likely get your job scheduled on 2 or more nodes. And if your software does not support running on multiple nodes, then you're basically going to type resources that'll be idle for on the other nodes for the duration of your job script. And you'll be charged service units for those idle resources. So make sure you either specify nodes or tasks per node. All right, time, the format's days, hours, minutes, second. You can leave the days off if you think your job's going to complete well within a 24-hour limit, or you can select 48 hours instead of doing 2 jobs, or however you like to do that. Memory, capital G for gigabytes. The max 488. We'll show you how to figure that out on specific nodes, compute nodes. Job name, avoid spaces. These are the output files we talked about earlier. Partition, if you need to specify a partition, put that in this. Remember, all these begin with pound SBATCH, all caps, and then partition equals, you give it a partition name. Generally, that's for like the GPU queue, or the PVC queue, or PVC partition, GPU partition or PVC partition. For non-GPU jobs, you don't need to specify a partition. Okay. Gress, this is if you're going to request a GPU or an accelerator. We have the format is -- gress equals the GPU, the type of GPU, and the number of GPUs. Also, you want to make sure the software you're using supports running on more than 1 GPU. If you want to change this to 2, make sure it supports running on 2. Otherwise, your resources are idle, and your charge service units for idle resources, and those are held up by your job, so no one else can use them. So make sure your software supports multi GPU usage before you configure or before you change this number to 2 or more. And then you'll just also need these two need to go together. You'll need to specify the partition as GPU for the H100s. And we'll show you some other how to determine which partition to use later on in the course. Accounts, if you want to change the account number just for this job, you can change it just for the job without changing the default project. Maybe you have more than one project. If you don't, you don't need to worry about this account parameter. If you want an email sent maybe when the job begins, let's just say you want to run an interactive job and the resources are busy and you don't want to stare at your monitor for 30 minutes, an hour, waiting until your job starts. So you can configure your email and the type of email. Basically, you would say mail type equals begin, all caps, and then that way you can go work on other things. And when your job starts, you'll get an email says your job is ready. Then you can go access your interactive session. You may have a couple of jobs. You may want to run one job and not schedule the second job until the first job is complete and it runs properly. You can do it this way. Dependency equals after OK, and then you input the job ID of the first job you submitted. You can get the job ID by running the SQ command --me. And we'll go over that later too. All right, partition, we mentioned that. You can see the partitions with the sinfo command. I'll show you that in a little bit. Once you submit the job, it's placed in a queue. You can search all queues. You can search just your jobs that are in the queue. CPU partition is auto-assigned, but if you're using GPUs or other partitions, you'll need to specify that partition. All right, these are the Your job script has the SBATCH parameters. That's what we saw earlier. There's a number of ways you can submit a job. Uh, uh, the recommended approach is to create a job script. That way you have a record of the commands that were used. And basically you just type in the SBATCH command. Once your job script is ready, SBATCH, and then the name of your job script. And that will submit it to the queue, place it in queue, and then you can monitor it to see when your job is the status of your job. You can also do this. Some users do this where they actually put the SBATCH parameters on the command line. And then at the very end, they just have a text file that has Unix command in it. So basically, it may be easier to do it the first way because you may not have a record of this, what's used on the command line. We do have a history of Unix commands, but that doesn't always get saved all the time. It may get overwritten and you'll lose those commands. So if you save it in a job script, you'll have a record of it. So in this second part, this one would not have SBATCH parameters in the command.sh script. These are accessed right here. T is the time, memory, G, job name. Here's another way you can do an interactive job. Basically what this does, you type in srun time, memory, SBATCH parameters, and then the very end you use --pty space bash, and you will actually receive your command line will actually once the job starts, it will go to the compute node, and then you're actually working on the compute node on the command line. You can also use the portal. We have a VNC app that you can launch a job and then you can access the command line there. But that is a little bit different. You actually just submit a job, and then from that job you get a command line, and then you can load any software. Particularly, it's useful for software that has a graphical user interface, or what we call a GUI, GUI. All right, sinfo, I mentioned this was a way to see the partitions. Sinfo, if you run that, so let's just go back to the command line. We haven't been, see if I can find my, okay, I was disconnected. That's okay. I can start a new session. And type in sinfo. Let me try to increase my font size here a bit. The Control L to clear the screen. Sinfo. Now you can see the partitions here, partition names. You can actually see sometimes these may be down for maintenance. You can see the time limit for the CP partition. You have a 3-day time limit. So if your job supports multi-core processing, it would be good to go ahead and select all the cores instead of running it on a single core, because it may take longer than 3 days on a single core, and it might complete in 6 hours if you use all 96 cores. GPU has a time limit of 2 days. We have a GPU debug partition that has a limit of 2 hours. There's other partitions. If you're familiar with this type of accelerator, there's different ways you'll have to code and run your code on these partitions. You can see this job size. That is the actual maximum number of nodes you can configure in a single job. Okay, so I was saying that the maximum job size is 64 nodes, for example, for a CPU job. For a GPU job, the maximum job size is 8 nodes, 8 compute nodes. And Control L, that's where we were. All right. Might be a little bit different from what's on the slide. Of course, this shows you the number of nodes active, inactive, online in total, offline in total. It might be a little bit difficult to read. We have other ways you can look at the main web page and see the cluster status. You can see ACES. At this time, this screenshot was taken. About half the nodes were being used with jobs, almost half the cores. You can see there are 537 jobs queued, waiting for resources. All right. So another way to see the type of GPUs available, configured and available. This is a composable resource. So we may have a node with 8 GPUs one day, and the next day we may have a node with 16 GPUs configured. So if you run this, when you start your session, you'll be able to see what's configured for the day. And you'll also see what's available, readily available for jobs. So just type in GPU eval. And you can see the configuration displayed first. For the H100s, we have 4 H100s per node, and we have 3 of those nodes. And we have nodes that have 8 H100s attached, and there are 2 of those nodes. We have some A30s, and we have the PVCs. The A30s, there's 2 A30s connected, and there's only 1 of those nodes. So the next column is what's available right now for jobs. You can see there are some H100 nodes here. This is the debug, GPU debug partition. And remember that partition has a maximum time, a runtime of 2 hours. So you're unable to use this resources. If there's only one H100 available and it's in the GPU debug, you'll need to limit that runtime in your job script to 2 hours. If you wanted to use a GPU, an H100 GPU, you can configure. Well, the maximum memory is 488. You can see some of this memory is used for a job that's used up 1 GPU. So if you wanted to use a GPU, say you wanted to use 3 GPUs, you can change your job script to use this much memory and this many CPUs. And if you can do that before someone else, your job must likely land on this node. The node name is AC049. So you can use this if the job before you submit a job, or if you submit a job and it's in waiting in queue for a long time. You can see how busy the resources are, and also what's available right now. All right, and also for CPUs, this is useful on our smaller nodes like ACES. Control L to clear. CPU eval. You can see we only have 73 CPU only nodes. That means these nodes do not have accelerators. There's 4 nodes here that have 488 gigabytes available. 5, 6. So there's 6 nodes that have all the cores and all the memory available for a job. But let's just say there was only 2 nodes available, and that was the first 2. And you scheduled your job to use all the cores and all the memory, and you just don't want to wait that long. So you can change your job. You can cancel your job script, and then you can reconfigure it to use 14 gigabytes of memory and 44 cores if that'll work for the software you're running. And then most likely you'll land on the resources here on this compute node. Max config. This one allows you to it'll show you the recommended Slurm parameters, configuring the maximum number of cores, memory, and time for a particular partition. So if you just run max config by itself, Control L to clear, it will show you the default for this max config command is the CPU partition. And then for the CPU partition, it will show you some SBATCH parameters. You can copy and paste these into your job script. Remember, the maximum runtime for a CPU job is a CPU only job. CPU partition is 3 days. So this will go ahead and give you all the SBATCH parameters. So you don't have to type them in by hand. And if you want, you can copy and paste this and then change the numbers. If you want to reduce this in half, and you can reduce the memory in half. But it also gives you some other information like the maximum number of nodes for the CPU partition is 64. And it also shows you how many service units will be charged to submit this job. So 6,912 service units to submit the job. If your job completes in half the amount of time, then you will be reimbursed for half the number of SUs. But if you submit your job for one day and it reaches one day and it hasn't completed, and you'll have to restart your job, and basically the processing that you've done so far will either have to be overwritten unless your software uses checkpoints. And maybe your software will create a checkpoint file whenever it reaches after a certain step. That way that step doesn't have to get repeated in case the job runs out of memory or something like that. And that's totally software dependent, or how you write your job scripts. So you want to oversubscribe or request days because you will be reimbursed for unused time. All right, you can run with any of these commands. You can run the -H or -help. You'll get more information. So let's just run Control L to clear. Max con, and you get tab to autocomplete -H. Get some information there. You can also see the SU rate per hour for each type of GPU. You can see the H100s charge you twice as many service units per hour as the A30s. So if you're able to use A30s, you can save on your service units if you're running low on service units. So let's find the commands to see what is the maximum number of H100 GPUs per node. So if you look here, if we want to specify the partition, remember the partitions. It's up here. Partition, the GPU partition, you would just do max config -P. -P is the option for partition, and these are the available partitions. You want to see for the GPU partition, you run it like that. I'm going to take clear so we can see that a little better. Max config -P GPU. So the maximum number of partitions is actually the PVC has, by default, it picked PVC because that has 8 GPUs. If you're not interested in the PVC partition, then you'll need to specify the partition, and the way you do that, or you need to specify the GPU type. So let's specify -H. So we want to specify the type of GPU, so use -G. -G H100. Okay, for the H100, you can see if you were to configure 8 GPUs, 8 H100 GPUs for the maximum of 2 days, and all the memory, all the CPUs and all the memory, it's actually going to cost 53,000 service units to schedule your job. So this is why it's a good idea to be aware of how your software supports running on the cluster. If it supports running on GPU, you could select GPU. You may want to also see if there are several steps for a workflow, and then schedule earlier steps that do not require GPU. Schedule those on a CPU only compute node, or schedule them on a CPU only job. Then you can, and when you reach your GPU processing part, you can create a job script that will just run the GPU part of your job. So what options to see the maximum for just one H100? So I'm going to scroll up here a little bit. You can specify number of GPUs. Okay, so that would be dash G. So I'm going to hit Control L to clear, go up arrow, and then dash G 1. So number of GPUs is 1. So you can see the number of service units went down from, what do we have here? I think I wrote what I had earlier. You can see the service units are now only 6,000. I believe earlier was 50 something thousand. So what we're seeing here is one H100, and the CPUs and memory have been scaled down to 1/8 of the total cores in memory because we have an H100 that has 8 GPUs. So this, again, it can be a starting point. Maybe your software relies mostly on the GPUs. You don't need that much memory. So do not schedule one GPU and all the cores and all the memory because there's other GPUs on the node. And those GPUs cannot be scheduled for a job if you've tied up all the cores and memory. Right. What about the bitware partition? If you're working with bitware, Control L to clear. You can do part-P. Bitware, if you're working with bitware, notice it adds a partition bitware for you. All right. Requesting all the cores in memory. Once you see how many cores and how much memory is on a compute node, there are several different ways to request all the cores in memory. If you request all the cores, then no other job can be scheduled on that compute node because there are no more cores available. If you schedule all the memory, then no other job can be run on that compute node. So if you, in this example 1, this is the output of max config. It will show you one node, one task per node, and that task will have 96 cores, 488 gigabytes of memory. If you're running an MPI job, you want to switch these numbers. Number of tasks is 96, and each one of those tasks will have one CPU. So be aware of running MPI jobs. You'll get more out of the more correct configuration by switching these two numbers, these two values. You can do n tasks. Some usually use n tasks, and maybe they'll do n tasks equal 1. CPUs per task is 96. Also, if you're using n task, make sure you select number of nodes. And here's another one. Yeah, if you're using n tasks, make sure you select nodes. Or if you're using n tasks, make sure you select n tasks per node so that Slurm knows how many nodes you want the job to run on. All right, single node jobs. Single node versus multi-core, single versus multi-core jobs. That's highly dependent on the software you're using or how you configure your job script. Again, 96 CPUs on the compute nodes. We also have a utility called TAMULauncher. If you have hundreds of commands, and each one of those commands just use one CPU, instead of running 100 different job scripts, you can run one job that will manage 100 tasks or 100 commands. That's what the TAMULauncher utility is for. We'll cover that in a little bit here. This is just basically what I said earlier. If you configure your job to use n tasks, but you don't specify nodes, of course, if you're only having one task, it can only run on one node. But if you schedule 96 tasks, then you could run on ranging from anywhere from one node, 96 CPUs per node, or 96 nodes and one CPU per task, 96 tasks. That's just to reiterate to make sure Slurm somehow knows how many nodes to run this on. We do get some help desk tickets where some Slurm will schedule a job of multiple nodes and the user is not unaware that software does not support running on multiple nodes, so resources are idle for the duration of their job. This is again just similar to the last slide. Kind of covered this earlier. Max config shows you requested or the recommended, or it will show you the recommended SBATCH parameters and scale the memory and CPU so that you're not tying up the entire GPU node. If you're using one GPU and all the memory, then the other GPU is unavailable. So just be aware of resource usage. If you're not sure, run a test job and look at the resources used, and I'll show you some ways to look at resource usage after your job is completed. How to change the number of GPUs? Basically, you just change this number here. This is the type of GPUs is always in lowercase H100 or A30. All right, single node. It's a single compute node, but multiple cores on that compute node. This is an example of a job script. You can request half the CPUs, half the memory on example 1. So you would put CPUs per task 48. Notice I have the number of tasks is one node. Half the memory is 244 gigabytes. If you do it this way, make sure in your command, whatever task you're running, make sure you specify 48 cores because that's what you've requested. That's the number of resources you've requested. And if you select all the cores and all the memory, then check the documentation for the software you're using, because some software by default will just use all the cores that are installed on the system and start using all the cores, and you don't want that to happen. So make sure if there's a threads option or a CPUs option, make sure you specify that and match it to the number of resources you requested. There's an environment variable called Slurm CPUs per task, all uppercase. This variable gets populated when the job is running. So it will take the value from up here in your SBATCH parameters. So basically you can have this in your job script. And if you want to change this, reduce this value later, maybe once you get an idea of how many CPUs it will use, then you only need to change it in one place. You don't have to go change it within your job script, because this environment variable will be based on whatever was submitted in this SBATCH parameter. All right, multiple node. Basically, you just change the number of nodes. Make sure you're aware of CPUs per task, and memory is going to be the same. The maximum memory per node. It's not the maximum total memory per node, so you don't have to multiply. You do not have to multiply 488 by 2. Remember, this is memory per node. And again, make sure Slurm has a way to calculate number of nodes. Otherwise, it could get placed on multiple nodes more than you expect. And there's some details here. You can read that to understand more about that. And bottom line is make sure your software supports multi-node processing, or that you've used TAMULauncher for a single node processing commands. Here's an example. Basically, you're using 90 tasks, 10 nodes, one CPU per task. So you're using 960 total CPUs, 96 per node, and it's 488 gigabytes per node. This is an MPI example where you would set n task to 96. All right, I mentioned TAMULauncher. There's some documentation in our knowledge base. There's a link at the top. We've had some issues with users submitting hundreds or thousands of jobs. That's not the way to do it. You want to submit one job or a job array. If you submit one job, you can use TAMULauncher that will if you have, like, for example, if you have 100 or 1,000 commands, you can submit one job with TAMULauncher and it will run those commands on a certain number of nodes, maybe for 10 nodes, and then it will manage each command. When one command finishes, it will grab the next command that's ready to be run. Good thing here, if your job times out, TAMULauncher remembers what the last commands that completed, and it will restart with the commands that have not completed. So it keeps track of that for you in case you run out of time. There's a status. You can run TAMULauncher -- status in the command file, and it will let you know how many commands have been executed and how many are remaining. All right, here's an example of in the box on the left. This is a commands file. You can call it whatever you want, commands.in, commands.txt. Basically, what we got, let's say, for example, there's 500 lines in here, and each line will use one thread. See, this software SBATCH specifies cores or CPUs by using the option threads. Again, other software might use the option CPUs. So you specify one thread for this command. I'm only showing a few of the 500 lines in this file. You have a second file. Second file is the name of your job script, run spades TAMULauncher.sh. If you're descriptive in your naming of your job script, then you will know kind of what's in here. It's a TAMULauncher script that runs the spades commands. And this example, we're going to run it on 2 nodes, 96 tasks per node, so that each node will be running 96 spades commands. Each one of those commands will use one task, and you want all the memory on each of those nodes. You will put your module load lines into your job script, not into your commands file. Your commands file only has the software commands. And then you add this line TAMULauncher and the name of your commands file. So in this example, you're going to have 96 times 2, 192 commands running at once. Uh, 96 on one node and 96 on the second node. If you can change this to 3 if you want, you can just use one node if you want. If you think the processing will complete in a day, or you can adjust the time accordingly, or just remember that you can, if you only complete 400 lines, 400 commands in the time period here, then you can submit a second job using the same job script. Just submit the job script the second time, and it will run the last 100 commands. It remembers where it left off. Let's just say each command can use more than one core or more than one thread. You can update that number here in your commands file, but you also want to change the number here. So in this case, you're going to run 24 commands per node. Each one of these commands will be using 4 CPUs, and I match the number of threads in my command with the CPUs per task. And again, all the memory, purge the modules to begin, load your modules, and then same command, TAMULauncher and commands.txt. You may have to add this OMP num threads. Some software uses this variable. Search the documentation for the software to see if you need to add this line, and this line would go right before TAMULauncher command after you load your modules. All right. I wanted to show you a way you can create all these commands. If you look, we've got a number of commands here, 500 lines. You can create this, and on the command line, some users will use an Excel sheet and export this. You'll just want to be aware to make sure you don't have control characters from using a Microsoft application. In that case, if you do, you'll have to use a DOS to Unix utility to remove those characters. But I'm going to show you some useful commands that you can use not only to create this job script, but also these are good basic Unix commands you can use for other things. So what we'll do is, in this example, if you have two input files, this is sequencing data, DNA sequencing data. If you have two files, each file, this is sample one, and there's two files that go with sample one, the R1 file and R2 file. So what we want to do is create these commands where you have spades. The first file, -1 is the first file name, -2 is the second file name. You have an output directory and you have threads. So we want to create this on the command line. So there's a few commands. And once you learn these commands, you'll be able to create a command file. So first we're going to go to scratch directory. All right, so I'm in my scratch directory. I'll do Control-L to clear. Now, make a directory seeks. What this does, the first command, make directory name seeks, and then these two ampersands means that if this first command completes successfully, then run the second command. Touch command will basically just create empty files. These files will be in the directory seeks, and they'll be named S1 all the way to S40, R1, and a second file for R2, and they'll all end with .pasqgz, which you can see will be these input files. So this is just a way we're going to create empty files. You can delete this later when we're done. But basically, if you receive sequencing data, you'll receive files similar to this. So make directory seeks. Touch seeks. S1 40. So this is a range from 1 to 40. And then R. And then we have just a range from 1 to 2. R1, 2. All right. Looks right. Let's go into the seeks directory. And then you can see these are just some blank files, empty files it created. You can do ls/lh and you can see the size of these files is 0. There's nothing in these files. All right, so we can create environment variables using the equal sign. So we're going to create an environment variable called file. So file equals, actually I need to back out of seek. So I'm going to go back now. If I was to see what's in the seeks directory, I could see that. All right, so file equals seeks. We want to grab the very first sample, the very first file. So file equals seeks S1R1 pasqgz. And these are all case sensitive. Actually, what I'm going to do, yeah. S1, sample 1. If I double click that, notice it my browser copied it for me, and if I hit Control V, that didn't work. You didn't copy for it. It's one R1. Okay, so I hit Control V. If you highlight it, it copies, and then hit Control V, and then it will paste what you copied. That will save you from having to type in dots and dashes and underscores. Okay, so now we create an environment variable called file. Let's see what's in the variable. Use the echo command, and then you'll need to use a $sign this time to display the contents. So echo file. Now you can see this is the contents of this variable, and this variable is only going to be valid for this session. If I was to open a new terminal, this variable is not in the other terminal or the other command line. You can type in, there's a Unix command called base name. That basically this will give you the name of the file without the directory path. So base name file, you can see it stripped off the path. Sometimes the path is really long and all you need is the file name. So just give me the base file name. And what we're going to do is create a second variable called sample. And this sample is going to take the output of the base file name. So to run a command and capture that output into a variable, you can use the $sign and these parentheses. So sample equals base name file. Sample equals base name file. So basically running the base name command and capturing the output. And then we can see what we captured. So now we have a variable called sample that we can use. All right, so now using these braces, you can take the sample variable, this / means strip off all of this, remove this from the variable so that all we're left is the sample name. So it's going to strip off R1 FASTQGZ, and all you're left with is S1. So echo sample underscore R1. All right, let's make sure that's right. Echo equals sample / R1. Okay. So we want to echo. So this actually echoes sample, and stripping that off, it doesn't change the value of sample. So if I was to go up arrow to echo sample, you see the sample variable is still the same. So it's a way to, you're not actually changing the variable, you're manipulating the variable to remove some of the characters in the variable. All right. If you want to do a substitution, you basically use / what's in the variable and / what you want to substitute it with. So substitute R1 with R2. Echo 1 R2. So whatever's in sample, change R1 to R2, and you can see I've got the second file name. All right, so now we learned how to create variables, get file names, and manipulate variables a little bit. So now I'm going to do a for loop. So for file in SEEX, we use a star or asterisk as a wildcard for it matches any character up to R1 underscore R1 dot anything else dot GZ. So if type this in, this will begin the for loop. Type in do, and then after this, you have your commands. And then when you type in done, it'll basically loop through all of these files and apply all this stuff that we learned earlier about base names and substitutions. And this will create the commands file for you. So you can go through this if you think you'll be using multiple commands. This might be useful to you, but at least you can get familiar with some of these Unix commands that you might find useful for other types of applications. So for file and seeks, for file and *R1 dot *GZ. Now I'm only getting the first R1 because if I captured both R1 and R2, I would have the sample name twice. So I only want the sample name once. And then you start it with do read one equals file. So whatever first file it captures, we're going to create a variable called read one. Read two equals read one and substitute R1 with R2. Read one, substitute underscore R1 dot with underscore R2 dot. And get this right the first time. All right. Sample equals the base name of read one without the part that doesn't describe the samples equals. So it is important to know when to use parentheses and when to use braces. Parentheses is for running a command, capturing the output of that command. Braces is for manipulating the variable contents or the output of the variable contents. Read one, R1. Actually, we've got both of those here on this line. All right. And then echo spade. This is where you're actually going to echo the spades command. So echo spades.py. -1. It's going to be read one and -2, read two, -1, 1, -2, 2, -O. This is the output directory sample. Now this is a little different here. What I'm doing is I'm taking the variable and I'm appending underscore out to it. So the sample is going to be sample1 S1, and then I'm appending underscore out to that variable. And then threads one. So that will create each one of those lines, and then you can type in done. And the redirection sign, the greater than sign, will send the output to a commands.txt file. Okay. So there were no errors there. I got it right the first time. To see the first few, well, you can type LESS commands.txt. I hit the tab key to complete that command for the name of that file. And this will basically show you the contents of your file to the screen, one page at a time. And well, actually, it all fit on the screen. That's why it shows end at the bottom. And you can see now I've created my spades command, the input, first input file, second input file, the output file, and the number of threads. All right, so that command, I hit Q to quit. So my commands file is ready. And if I wanted to, I could hit up arrow, and I've already got this typed in, and I could go back and actually my cursor's not moving. Maybe that'll work. No, my cursor's not moving. But I can hit up arrow and then I can not sure. Yeah, I'd have to see where my cursor is here. I'm going to start a new session and see what happens. Okay. Maybe my other session will have. Looks like the cursor's correct here. But notice I don't have those. I don't have that command saved here in this session. The thing about exit, oh, this is login 1. This is a different login. So let me try to log in again. Let me just start a new session. Maybe I'll log into 1 this time. Oh, still on 2. Still on 2. Well, it's on login 1, so we'll just stay here. Next time I log in, this will be in my histories command. My command's ready, command file's ready. And so that might be useful to you to create a commands file. If you could do it in Excel, just be aware of control characters. In that case, you would have to use this command to remove those characters. Basically, you say DOS command, DOS to Unix in the name of the file, and it will remove those characters for you. Those characters will cause Slurm to fail. It doesn't recognize those characters. It doesn't strip those for you. So make sure those are not in your commands text file. All right, this is another way. It's a little more complex. I have it here as a reference. I don't remember these every day. I don't use them every day, but I have a file, or actually I use this slide to remember how to use these other types of text substitution for variables. So you can work through this. Basically, some similar commands: create a variable, echo what's in the variable. This actually will strip. Let's see. So single percent will drop part of the variable from the last occurrence of substring. So whatever substring is, maybe use the term template or samples, whatever's in the variable name, it will strip off the last instance from that instance until the end. That's what the star is for. So you might find that useful. And I'm not going to work through this, but generally this is where we take a break. We'll take a 10-minute break and we'll be back at 3 o'clock and continue on, and we'll move on to the next slide. But you're welcome to work on this for the in the break, and it's easier to follow along once you understand the previous commands. At the end, you may never use this, and but you know it's there in case you want to come back to it. All right. So when we come back, we'll talk about environment variables, and we're back at 3 o'clock. In the second part, we'll be covering, start out with a few environment variables, and then we'll submit a job script and see what resources it used and what resources were selected. There is an environment variable called tempdir, TMPDIR. This is not on the login node. It's created when a job script is launched in that temp directory. On the compute node, this is not the scratch or home file system. It's a compute node that's on the actual computer motherboard for each compute node. So that has a disk that's 1.4 terabytes of space. That's useful for writing a lot of temporary files. Some software you can specify the temporary directory, and you can set that to the $tempdir all uppercase. Those files do not count against your quota, so you can write 100,000 files there if needed. And then when your job is completed, that directory is deleted. Notice if you want to use the entire 1.4 terabytes or more than 1 terabyte, you should request the entire compute node, because that disk space is shared between all the jobs that run on each node. So if there are 10 jobs running on a node, they may all be competing for space on the temp directory. So if you need to use one or more, between 1 and 1.4 terabytes of space, you reserve the entire node, and you can do that by requesting all the cores and all the memory. This is an example of the SAMTools utility tool. You could, during the sort processes, it uses a temp directory, and you can specify that with a dash uppercase T. We went over Slurm CPUs per task. You can add that in the commands like we showed earlier. If you're running a job array, you can capture the task ID with this variable, and you can read more about job arrays in our knowledge base. if you want to capture the job name, you can use this variable. Basically, it takes whatever you put in the SBATCH parameters of your job script. You can actually get the node list if you're interested in that. Sometimes software may need the node list, so you may need to capture this list, and you can use this variable. Job ID, that's determined at runtime, so you don't know what the ID will be until your job is launched or until your job is scheduled. Once it's in queue, it will get a job ID. You may need to use user. Basically, it will give you your username. Scratch is very useful. It takes you to your Scratch directory. Remember, that's the one that has 1 terabyte of space, more than your home directory. So if you're running, you'll most likely want to run your jobs starting in your Scratch directory. You may need to set this variable for some software that uses OMP num threads, and the way you do that is you add this line, export OMP num threads with no $sign in front. You're actually assigning the variable so you don't use the $sign, and you set it to the number of CPUs per task, or CPUs that you've configured in the SBATCH parameters. There's another one you may find useful, PWD. Basically echoes the prints the working directory. All right, so let's start by, we have a utility called GCA templates. These are template job scripts that are configured to run a specific bioinformatics software. You don't have to be familiar with the software to do this exercise. And basically, you'll see you can get an example job script and submit the job script. It has some example data, and then you can get an idea of submitting a job, what it's like to submit a job, monitor and view the resources afterwards. So the first command, we're going to make a directory in our Scratch directory called Slurm class. You see where my session was terminated. I'll start a new one. All right. And then I'm going to CD that directory. So I'm going to do up arrow, come over here and just change this to CD. Okay. Now you can see I'm in my Scratch Slurm class directory. You just run this GCA template and you'll get this menu. We only have a couple of categories here. What you want to do is you can enter one and then continue through till you find FastQC, or you can hit as to search and you type in FastQC. I'm going to do the first way, and then I'll go back and show you how the search works. So the first one, it's going to be FastQ files. So type in number 1, hit enter. And then this is quality evaluation. So again, it's number 1. The task is quality evaluation. And the tool is FastQC version 0.11.9. So type in 1 again. And then sometimes we have software that's configured to run with 1 or multiple input files or multiple nodes or certain other parameters, certain other options that the software offers. But in this example, it only uses the default, so we have one option, so select one. So now it says copy script to current directory. The script name you can see up here, it's run fastq version 0.11.9 on ACES. And I'm going to type in Y for yes, copy it. So we do ls. There you can see the JavaScript example template script. There's some information to remind you that this is just a template, an example. The software offers a lot more commands, a lot more options. You should probably read the documentation to see if you need to add or remove options, change SBATCH parameters, and increase time for your data. All right, so I'm going to do this again. Show you the search function. So S for search. FastQC, you can see it took me to the tool name FastQC. And then basically it's where we were last time. Type in 1. And then there's only defaults. Now I want to copy script to current directory. I'm going to click yes again. Do I want to override it? It's already here, so I'm going to just type it no. All right. So now we're back to our job script, and let's see what's next here. All right, let's talk about service units. I mentioned that earlier. Service units, these are what you have in your project. You type in my project, and you can see your service unit balance. I'm going to look at my default account, which has a Y. The default column, this is my default account number. It's for fiscal year 2026. These have to be renewed each fiscal year. You can see this is actually a larger allocation, probably for multiple users. Basically, it shows your allocation total, what it started with, how many are used or pending on jobs right now, and this is the balance available. And it's got PIs of that project. So a service unit is one service unit per CPU per hour. That's the charge rate, or one service unit per 5 gigabytes of memory, of requested memory per hour. So if I was to select 1 hour in this table, this is just describing 1 hour. All of these are 1 hour. If I was to select one core, 5 gigabytes of memory, and no GPUs, there are 0 SUs charged because we don't have any GPUs, and we only charge one service unit because you requested one CPU or 5 gigabytes of memory. If you increase this to 6, you're in your second chunk of memory, so now you're going to be charged 2 service units. So the minimum charge for one service unit is 5 gigabytes in 1 core in 1 hour. If I was to request 1 hour, 1 core, and all the memory, you'll be charged 96 service units. The same as if I request 1 hour, 96 cores, and all the memory, 488 gigabytes of memory, you're still be charged 96 service units because basically you're being charged for the entire compute node, whether you request all the memory or all the cores. So request both all memory and all cores until you're familiar with the software and how much and the number of resources that we'll use for your type of input data. Now, if you select a GPU, let's just say I'm selecting one A30. There's two A30s on, generally two A30s on compute nodes. So I'll reduce the amount of cores and memory to half. You'll be charged 62 service units per hour for the GPU, and then you'll be charged for the cores and memory. So basically it comes down to 112, the calculation of using one A30 and reducing the cores and memory. You can reduce it even further if your software doesn't rely heavily on number of cores or a lot of memory and mainly relies on GPU processing. You can reduce this even more to reduce the service units charged. And this is a link to where you can see the more about service units and the charge per GPU. All right, so we have a utility called max config, which will estimate the number of service units to launch a job script. So we're going to use this max config for the file we just created, our template file. So you would run max config and -F option and then the name of the file. So max config, I hit tab to complete -F. I'm going to type in RU and hit tab. So the tab will complete the name of the file. And then let's see what it tells us. It shows us the calculation for your job script is one service unit because you're requesting 2 tasks and for half an hour on one node is charged 1 service unit. Okay, so this will give you an estimate of service units charged without submitting the job. Maybe you want to see, you want to keep reducing CPUs and time until you can fit it into the number of resources you have left in your balance. And this is a way you can do it without submitting the job each time. All right, so let's go ahead and submit this job. The command is SBATCH, and then you can type in RU, hit tab, and it will complete the name. And right after you submit the job, you want to see the status by typing SQUEUE-me. So SQUEUE-me. Right now, if I type it, there's no jobs running. SBATCH. That submits the job. If I go up arrow a couple times to my SQUE command, now I can just go up once. It's pending. It'll take a minute or two to schedule resources. If you need to cancel the job, you've got a job ID now. Here's the job ID. You can type in cancel and cancel the job. I'm not going to cancel that. So we do have 2 tasks and 8 CPU, no, 8 gigs and 2. So we do have some nodes available. It just may take a while to get started. Now it's running. All right, this is really quick. It takes less than a minute, I believe. While it's running, you can do PE stat -u and then that variable to show you. I think it's because I have more than one user because I'm on staff. So you can type in that and it will show you basically the compute nodes your job's running on. It will show you the CPU load. So if you scheduled all the cores and all the memory, this will show you basically this in this first line that this job is running. Actually, this job is configured to run on multiple nodes. The first node is using 46 out of 48 cores, so it's almost at 100% capacity on all cores. So it's running really good, really well. Here's one that's white, so that's the best you can get. Pretty much 48 CPU load for all 48 cores. 45 is just showing you in red, but still 45 CPU load for 48 cores is really good. If you see 0.01 CPU load on 48 cores, it's probably because you're at that point, the commands are only running on one CPU. But there may be a step later in the software that uses all the cores, and then maybe there's another step where it only uses one, then it just repeats that. So this is updated every 3 minutes, so it doesn't help to watch it every second. You can set an interval to watch if you want. This information is not saved, so it's once the job is complete, that information is gone. Again, remember, if there are multiple jobs running on this node, this is for all the jobs, not just your job. So we'll show you how to figure out just for your job. So I think our job is probably complete. Up, still running. All right, maybe it takes a few minutes. Here's an example. Actually, it took 4 minutes. This is an example of the SEFF command. It's basically Slurm efficiency and the job ID. So SEFF, I'm going to copy this, double click, and then Control V to paste. And now it's showing me my job is running. The state is running. It's running on one node using 2 CPUs. So far, it's been running for 2 minutes, 52 seconds. Memory efficiency, that's not going to be accurate until the job completes because it doesn't really know how much time the job will take. So when this job is complete, you'll be able to get the efficiency stats. And the efficiency stats is for your usage only, not for other jobs that are on that compute node. So you can see in this example, CPU efficiency of 99% is really good. During the 8 minutes it took to run, 99% of each of these cores were at almost 100% processing capacity or CPU load for the duration of the job time. And it used 1 GB of memory. So scheduling 8 GB was good. I can probably drop it down to 5, but you're still going to be charged for 2 CPUs. So you can leave it at 8. So when the job's complete, that's one way to get resource usage. Another way is the my job command. So basically, my job will show you a lot more information. Some of this information is taken from the SEFF command. And then there's other information, including if your job failed, it can be some debug messages. It'll let you know if your JavaScript has CRLF characters. It'll let you know if your job is pending due to a scheduled maintenance. And I'll go over maintenance, scheduled maintenance in a little bit. And then it'll also let you know if you reach disk quotas or file quotas. So let's just see if my job's still running. Up, it's complete. And there's the output files. I remember I said that the output file would be named standard error dot file name and then job ID. And then there's a standard output. Okay. We can still get information. Now let's do the SEFF command. Now we're going to get CPU efficiency. This was 97, which is still really good for 9 minutes. And it gives you some more information. 12% of the memory of the 8 gigabytes was used. That shows you could probably drop it down, but still will be charged for 2 service units. This particular job used two cores. There were 2 files to process. So one file was processed as 1 core, and the other file was processed with a 2nd core. In this particular software, FastQC, if I was to select 96 cores, it will not process a lot quicker because basically you can only use 1 file per core. I have 2 files, so just select 2 cores. All right, my job will show you a lot more information. Let's see what we get. I'm gonna copy this job ID. I'm gonna hit Control L to clear. Paste the job ID. All right. So it shows you what account was used, the node list, efficiency, submit time, start time. So it took less than a minute to begin, but it took 4 minutes, almost 5 minutes for the job to complete. It also shows you in which directory you submitted the job, and it also shows you the commands you used. Now, let's see if we have this. Okay, so the -s command, my job script, my job ID -s, will give you the output, what we saw earlier, but will also show you the original job script. See, this is the job script, the contents of the job script. We didn't really see this earlier, but let's see. You can see this is the job script. I'm just printing the job script to the terminal, but basically it saves it. So if you were to want to go back and you're interested what your job script looked like, maybe you accidentally deleted your job script. If you know the job ID, you can go back and get the original job script, and you can copy and paste this into a new job script. So that's using the -s command. And use my job -h, and it will show you other options. You can show your quotas, you can show your project accounts, you can find the directory in your home directory that has the highest file count. Usually that's a hidden file, starts with a dot, sometimes it's .cache, maybe .config, maybe not .config, .cache. .conda is another one that gets full. Those, remember, we move them to scratch directory and create a symlink in the home directory to point to the scratch directory. Or you can run -f. F shows you everything that the script offers. You can see there's my accounts. It also showed me which directory has the most files. I have a Mozilla directory that has 2,670 files. This is probably when I'm using software application that's accessed through Firefox on a compute node. And if any of these are nearing or past reach your quota, they'll be highlighted in red. So that's my job. There's also another utility called job scripts. I'm sorry, job stats. Job stats basically will do some monitoring in the background. You send it to the background by using the ampersand. So in your job script, before you run your actual command, you'll run job stats space ampersand. and it will monitor CPU usage, memory, and it will also monitor GPU load and GPU memory usage, and it will create graphs for you. So you basically set it in the background, run your commands, and after all your commands are done, you run it one more time don't set it in the background the second time. Run it one more time, and this time it creates um, images of usage. And let's look at this. This is a GPU job. In the GPU job, I scheduled two H100s. And if you look here on the usage here, memories in blue. So we do have some, the H100 GPUs have 80 gigs of memory. So for the most part, it was using about 40, maybe 50 gigs of memory on it, and some spikes here, and then of usage. And then the percent load on the GPU, that's the core load, the percent load on the up to 100%. We've got you can see it goes up to 100%. This is on GPU 0, which is the first GPU. The second GPU is index GPU 1, and there's no activity on this second GPU. It's all 0. That's actually the 0 line for no usage. So if you were curious as to whether your software is using both GPUs and you run this job and you get this type of image file, then you either need to change the way you run your commands so that we use both GPUs, or you can reduce it to one GPU and just use a single GPU. All right, so here's the ACES dashboard. There's a lot of useful information here. This is basically what's on the command line. You can also get it straight from the dashboard. Your quotas and your project account balance. You can also do a little more, like request a quota increase directly here. This is where you do want to request increases. This will create a ticket for us, and then someone can work on that and let you know when the increase is made. That'll be reflected here. We also have a way to acknowledge us. You could, if you click here, or this is just a slide, but when you click here on the portal, when I go back, let's look at that. It's HPC Mosaic. All right, so if I want to change my default account, I can do it here. And then this might be useful. GPU, how many use, how many total. Doesn't really break it down per GPU, but you can get an idea. GPU debug, there's actually at least one GPU available here because you can see there's only usage of use 98 total 288. Actually, that might need to be corrected. There's only 2 GPU nodes, I believe, or GPU debug nodes. Oh, that's cores, sorry, 98 cores. All right. Here's where you make a request to increase. If I wanted to increase my home, notice I can't. There's not because we do not increase home directories, but I can request an increase in my scratch directory. Is this more than 10 and longer than 6 months? Let's just say no, I'm working on a project. I'm going to get it done and then offload my data from the cluster to free up disk space. So I'm going to work on a project. Lasts me a couple of months, then I'll be done. Fill in all this information and submit this, and then we'll get all the information we need to increase this quota if it's approved. You can see jobs running. I don't have any jobs running. Here's the HPRC acknowledgement. If you click here, it's basically we have a list of publications that acknowledge us. Some are PhD thesis, some are conferences, some are journals, technical report. So we do need to go back and query the last few months. You can see we had a big spike here going up. It should continually, ideally, keep increasing. But We did have a graduate student, or a student worker that worked on this, and he left in 21. So that's why we kind of haven't. That's when we have not so many here in the last few years, but we do have a lot we're working on to get this updated. So you definitely want to let us know. First of all, you want to acknowledge us. Here's the text you can use. And then once you acknowledge us, let us know and we'll add it to our list, our graph here, and you can do that right here. Send us the DOI and BibTeX if you have it. All right. All right. Debugging. If you configure 600 CPUs per node, there's not a compute node that has 600 CPUs, so you'll see something like this. Nothing like that exists. So just cancel. Well, looks like the job failed, so you need to reschedule or reconfigure that job script. Pending jobs. We talked about sinfo and GPUval. So maintenance, you can run maintenance command at the terminal. Control L to clear. Maintenance. We don't have a scheduled maintenance right now. If we do, it'll give you the countdown, so you can change your job script so it'll fit within that window. And usually a maintenance will last a day and everything stops. Processing stops while we make changes to hardware, software, or whatever we need to update. And so you can keep track of that. And if you submit a job, if you're on maintenance and it shows you this, we have an 11-hour maintenance scheduled to start in 2 days, 6 hours, 41 minutes. If you submitted a 3-day job right now and you saw this, your job will not run until after maintenance is complete. So you don't have to cancel it. You can keep it in queue and it will just run after when maintenance is complete. Or you can cancel the job, change it to 2 days, 6 hours, and hopefully it starts within 41 minutes. And that way you can probably squeeze it in before the maintenance starts. All right, exceeded job memory limit at some point. That just means you need to schedule more memory in the --mem field. Search the log files. You might see out of disk space or no space left on device. Usually the second one is for the temp directory. All the 1.4 terabytes has been used up. Check your quotas. Jobs are failing. First thing you want to do is check your quotas. You can do that easily. Make sure none of these have been reached. I believe a star, an asterisk will be next to one that has reached the limit. Reduce your file count and disk usage by deleting temporary files, non-essential files in your scratch and home directory. You can create a tar-gz package. You can look online how to do that. Create a tar-gz package of a directory and download that. Once you verify that you have all the data in that tar package, you can remove the data from the cluster, free up space. It's good to create a tar package instead of trying to download an entire directory, just because it can be a lot quicker and you have it packaged up. Maybe you have a project packaged up. It's more portable than copying an entire directory structure. All right, interactive apps. You can access these through the portal. And let me go show you about those. Interactive apps. We have a number of interactive apps. VNC is the one I mentioned earlier. This will launch a terminal session, kind of what we see here. The difference being that I'm going to do CPU only. I'm going to launch that. All right. The difference here is if I close this browser, this session is lost. But I'm creating a session on the compute node by using this VNC app. So that session will remain open as long as you have time remaining and as long as you don't delete it. So if I start this session, I go and work on it. I'll do that in a second. And then if I need to go home and I can complete it or check the status at home, I can open the portal at home and log into this session. So if I click Launch VNC now, you can see I have my terminal here. And I can do work here. If I need to, I can log out of this computer, log out of my computer, go home, log into the portal, and my session will still be there. And then at home, I can connect to the same session, and it will still be running as long as I have time remaining. So that's very useful for interactive jobs. Also, if you have your own software that has a graphical user interface, you can launch it here, and that'll be a lot smoother than trying to tunnel it. Of course, we can't tunnel anyway, so on ACES, so this is the best way to run your GUI application. We do have some GUI applications already configured, like Chimera X, ImageJ, some imaging software. All these pop up GUIs. And then when you're done with this, click delete because it will run and charge you service units for the next 58 minutes. So I'm done. This is the session. I've got two of them open. But this is the session when I click delete. I want to delete it. Yep, I want to delete it. And then notice that the session goes away. You have no more active sessions. All right. Those are interactive apps. Here is the Drona Composer. This is a way to create a job script for a specific environment. Drona workflow engine. Let's just say you're working with R. You can select an R version, and then gigabytes. Let's just say 24. Runtime. Let's just say 1 hour. Oh, 1 hour. Project account. We'll leave that. Job name. Now you can see the directory where it will be saved. You can change this directory if you need to. Select a new directory. I'm going to leave it like that for this example. Now, you can see some of my other jobs that I ran in the past using this Drona Composer. If I do preview, it shows me the job script. All right, let's see. It doesn't show you SBATCH parameters. Those are configured in the background. But basically it shows you loading the modules, going to your run directory, and then running your R script. Here you can do other things like maybe you wanted to use job stats with this, and then so maybe you want to start job stats, get a graph of resource usage, and then run your script, R script, my script. Now you have a script called R, myscript.r, has your R commands in it, and you could submit the job. So you can do that with other environments, a generic environment. If you just want to pick a module. Here's the FastQC module. What did we do? 8 gigabytes last time. Do 1 hour. Task 2. See what it gives us. This one does give us the SBATCH parameters, which you can change if you need to. Let's say I wanted to do 4. And then you can add you'll need to load the FastQC module because this is a generic job file. Oh, I didn't add it. Go click add. There it is, add. Now let's preview it. So it did load the FastQC module. It loads web proxy in case the software needs to query the internet. Usually some software will query looking for a license, or maybe it will query to see if there is a newer version of the software available, which is basically just let you know if there's a newer version or not. And that'll let you know without you having to go search the web for it. It'll let you know. You may want to update to a new version. Then you add your commands in here, your input files, kind of what we had. Oh, fast QC. So cat will print the contents to the screen. So basically you would do something similar to this. Basically, you just add your commands here and then submit that. And then you can see if you refresh after you submit, refresh, and you'll be able to see the job history, and these are saved. All right, so I wanted to show you one more thing here. To edit files, let's go to Files, Scratch. Now let's go to Slurm class. And then here's our template JavaScript we copied. I can edit this script here if I need to. Let's say I want to make some changes. Let's say I do want to make it 5 gigabytes here. 5 gigabytes, because I know it only took, what was it, less than 1 gigabyte, I think. Now, since I made a change here, I do need to click Save to make sure I save my changes. Now, if I close this, or I don't have to close this, come here, Control L to clear, and I'm going to output the content to the screen, and you can see my file was updated. If you want to learn VI, VI is a text editor for the command line. You do have to learn some commands. There's a kind of like the browse mode, and there's the edit mode. I think it maybe is to get into the edit mode, you tap I for input, escape to get back out, and you gotta hit :Q to quit. That's if you didn't make any changes. So there's quite a number of commands, and it takes a little bit longer to learn VI. But if you don't have a lot of editing, or you just want to work with a GUI or a graphical editor, you can use this to edit your files. You can also use this to, what can we do? View? I don't know if we can view HTML. I didn't view HTML correctly. You can also rename it, download it, or delete it. And then you can definitely browse here, create a new file, a new directory. You can do some uploads here. Uploads generally is for files less than 2 gigabytes. If you're going to use more than 2 gigabytes, come to our wiki here and type in Globus Connect. This is a utility. It's web-based. You do need to install something on your computer, local computer, if you're uploading from your local computer. And basically, it schedules transfers, or maintain file transfers for small files or large files greater than 2 gigabytes, or for an entire directory. And basically, you get two panels: your local computer and your cluster, like ACES, for example. And you can drag and drop files, or you can click on them, select them, and then click Start. So you do need to do an installation. There's also a command line for this if you want to work with the command line. If you're using it often. All right. Oh, we covered that. The history down at the bottom. Make sure you push refresh to see the history. All right. So that is the last slide. This is our contact information. We have a survey here. Please scan this and take our survey. Let us know how you like the course. If you want something added, maybe want us to show a little bit more details about a section in this course, or maybe you have just want to have comments about the course, maybe something you missed or didn't understand, to make it more clear in our documentation, that will help us. And then if you have any information or any questions, make sure you let us know when you submit a help desk ticket. Let us know which cluster you're on, and let us know the job ID. From that information, we can get most of the information we need to help you debug your job. Because we do have more than one cluster, and we do have more than one cluster that for access users. So let us know the cluster name and the job ID. And you could submit, let's see, we've got two different ways. You could send the email to our help@hprc.tamu.edu, or you could go to the dashboard and you can click Get Help. Help requests. What do you need help with? I need software installed. I need to have a problem with my account. Maybe I need to transfer SUs from, if you're a PI, you can transfer SUs from a user to one of your researchers, and you let us know the number of service units. You can also, if you're a PI, you can use this manage accounts, and you can do the transfer yourself. If you have researchers under you. I believe we still have to add researchers under you, but once they're added, when you apply for your account, then you're able to manage the service units that you have. All right, that is it. If anyone has any questions, feel free to unmute yourself and ask questions, or ask in chat. We'll hang around here for a little bit. Otherwise, just thanks for attending, and we're always here to help if you have any questions about accessing the cluster, debugging jobs, software installation usage. Just let us know.